What if a traveler from another star system cruised through our cosmic neighborhood and kept behaving in ways that puzzled every telescope that looked its way? Welcome to Adventure into the Unknown, where we explore the world's most fascinating mysteries and untold stories. On July 1st, 2025, the Atlas Survey Telescope in Chile flagged an object unlike most comets or asteroids. The object's trajectory and speed revealed it to be interstellar, meaning it did not originate in our solar system, making it only the third confirmed interstellar visitor after 1I, Oumuamua, 2017, and 2I, Borisov, 2019. From the first published data, astronomers began intensive follow-up observations to learn whether this new visitor was a normal comet, a peculiar rock, or something more unusual. Early images showed a fuzzy coma, a cloud of gas and dust round a compact nucleus. High-resolution pictures from Hubble helped tighten size estimates and revealed details of the coma and dust cocoon. Some teams reported a reddish tint to the coma and signs of dust and ice grains. Other spectroscopic measurements later detected water in the coma. Importantly, different instruments give different constraints. Initial size guesses varied, and follow-up imaging refined those estimates downwards in some cases. Hubble's recent observations were key to narrowing size and activity estimates. The object follows a strongly hyperbolic, unbound path, a straight, fast arc that indicates it will not be captured by the Sun's gravity and will leave the solar system. It will make perihelion, its closest approach to the Sun, in late October 2025, and its closest approach to Earth is far beyond any danger zone, roughly on the order of astronomical units. So, there is no impact threat to our planet. These orbital solutions are based on many observatories' data and are continuously refined as more observations arrive. Compared with the two prior interstellar visitors, this object stood out because of its relative brightness and the scale of the coma, which gave astronomers more signal to study composition and structure. That, combined with its fast passage and the timing of its perihelion, made it a high-priority target. Space telescopes and major observatories mobilized to collect spectra and images while the object remained observable. Those coordinated observations are what let scientists test hypotheses about its nature rather than rely on guesswork. If you're enjoying our journey, please take a moment to like, share, and subscribe. It's free and it helps us create more incredible adventures for you. Thank you for your support. So what do scientists say? The cautious answers: let the data speak. Spectroscopy and multi-wavelength observations look for the fingerprints of water, carbon compounds, and other volatiles. Instruments sensitive to the near and mid-infrared, as well as ultraviolet and optical spectrographs, have been used to search for water vapor, CO, and common cometary molecules. Some teams reported water in the coma and organic-like spectral slopes consistent with irradiated organics. But these are measurements with uncertainties and active analysis is ongoing. Telescopes like Webb and Hubble play complementary roles. Webb's infrared sensitivity can reveal molecular ices and gases, while Hubble and ground-based spectrographs constrain visible and ultraviolet signatures. Unconventional voices have suggested non-natural explanations. Prominent among them is Harvard astrophysicist Avi Loeb, who has argued that some interstellar visitors warrant careful consideration of technological origin and hypotheses, and even suggested creative ways to learn more, such as repurposing existing spacecraft for flybys. These ideas are hypotheses, not conclusions. The mainstream scientific method requires reproducible evidence, peer review, and multiple independent measurements before extraordinary claims can be taken seriously. The mainstream agencies and observatories continue to present data-driven, conservative interpretations while investigations proceed. Intercepting a fast interstellar visitor is extraordinarily difficult in practice. Launching a new, purpose-built mission takes years. Existing spacecraft could theoretically be retasked, but fuel, pointing and timing constraints make such maneuvers risky and expensive. Proposals to investigate with probes already in the system, for example, repurposing long-lived probes, have been discussed publicly, but engineers stress there are serious feasibility challenges. Still, the rare opportunity spurs creative conversation about what current technology could do in an emergency scientific scenario. Good science separates data, interpretation and speculation. Observatories publish spectra, brightness measurements, and orbital elements. The community then subjects those data to independent analysis, modeling, and replication. Claims about alien technology should be treated as extraordinary and held to extraordinary standards of evidence. At the same time, open-minded, hypothesis-driven inquiry is part of science. The balance is rigorous skepticism plus curiosity. That's the approach researchers are taking with 3IATLAS. Gather the best possible data, test multiple explanations, and be transparent about uncertainties. In short, 3IATLAS is a rare, fascinating visitor that gives astronomers a fresh chance to study material from another star system. The best path forward is patient, careful science. Continue observing, refine models, and let the data guide conclusions. We've learned over the past decade that unusual objects can force us to rethink assumptions, but they also reward disciplined inquiry. What do you think? Natural interstellar ice and dust, or a manufactured object that will rewrite textbooks? Share your thoughts below, and remember, evidence wins the argument, not speculation.